In this work, we present a method to optimize kinematic design parameters for a parallel surgical robot in order to maximize the ability of the robot to visualize relevant anatomy inside a patient's body. We consider optimizing kinematic design parameters for the Continuum Reconfigurable Incisionless Surgical Parallel Robot, or CRISP robot. The CRISP robot consists of 2 or more needle diameter tubes that are inserted into the patient's body and assembled into a parallel structure via snares, which allow the tubes to grip one another. The tubes are then manipulated robotically outside the patient's body, changing the shape of the structure inside the body. In this work, we consider the case where there is a chip-tip camera affixed to the end of one of the tubes, and it is the desire of the surgeon to visualize patient anatomy using that camera. One such application is diagnosing the cause of pleural effusion. Pleural effusion is a medical condition in which fluid fills the space between the chest wall and the lung. In order to diagnose the cause of the effusion, physicians must visually inspect the space. In this case, the tubes would enter between the patient's ribs and assemble into the parallel structure in the pleural space. We consider the optimization of a set of kinematic design parameters for the CRISP robot that are set prior to the surgical procedure. These parameters include the entry points where the tubes are inserted into the patient's body, as well as the snare grasping locations which dictate the parallel structures of the CRISP robot inside the body. It is important to consider these parameters as they can greatly affect the ability of the robot to visualize patient anatomy. Consider this 2D example here. With the robot entering the body at these points and with a snare grasping location as shown, the robot is not capable of visualizing much of the interior surface of this scenario due to the constrained motion caused by the red obstacles. If, however, we consider a different design with entry points here and a snare grasping location here, the robot is capable of visualizing a much larger percentage of the interior surface as it moves in a collision-free manner throughout the space. To optimize the designs, we leverage the global optimization algorithm Adapted Simulated Annealing, or ASA. ASA iteratively samples designs in design space and evaluates their quality in order to converge on a globally optimal design. Early in the design process, it may sample an inferior design, but as time progresses, it will converge on the optimal design. In order to evaluate the quality of a design sampled by ASA, we leverage a sampling-based motion planner. We keep track of the points on the interior surface of the anatomy which are visualized at each step of motion planning. This allows us to consider the capabilities of a design to visualize the anatomy via collision-free motions. We evaluate our method in 2 scenarios. In the first, we consider an ellipsoidal volume with cylindrical obstacles. In the second scenario, we consider the case of visualizing the interior surface of the pleural effusion. Here we segment the effusion volume from a CT scan of a real patient with this condition and consider the optimization of CRISP robot designs in order to enter the volume in between the patient's ribs and visualize the space. In both cases, the method performs well, allowing us to go from designs that are able to visualize a small portion of the anatomy, such as is shown here for scenario 2, where the purple points are the visualized points, to designs which are able to visualize a much larger percentage of the anatomy, such as shown here. Our method, which leverages ASA and motion planning, allows us to optimize the kinematic design parameters for the CRISP robot. This results in designs which are able to visualize a large percent of relevant anatomy.